Welcome back. So we got up to just trying to decide what kind of equations are the Euler equations. So in particular we want to try and classify them about whether they're elliptic, hyperbolic or parabolic. Now that's not particularly interesting just to classify, but we're interested in the physics of these equations. So what is the physics expressed by our rules for conservation of mass, conservation of momentum, conservation of energy? So how do those rules come together to tell us how fluids actually work? All right, so the tool we're going to use for this is a pretty common one in all of physics. It's just called linear analysis. Linear analysis, or a perturbation study. So we're going to assume some small perturbations about some reference state. So we've got some equilibrium state, and we're assuming that we've got some small perturbation. So for example, the density equals the background density plus some small perturbation, which we'll call delta rho. The velocity is some background velocity, which we'll take to be 0, as we'll take a medium at rest, plus some delta v. And we take something like pressure, is P naught plus delta P. And well, hopefully you've come across this in other areas of physics. So the game is to insert these into our equations and what you call linearize. So linearize just simply means drop terms that are second order or higher. So let's do this, and we're also going to define one more relationship, which you're going to see why it becomes important later. But for the moment, I'm just going to define a constant as being the relationship between, actually it doesn't have to be a constant, as just defined as the ratio of the pressure perturbation to the density perturbation. So in other words, the delta P is just related to delta rho by some other variable. So in general, this should be expressed as a perturbation equation as well. So sound speed is sound speed naught plus delta sound speed, for example. It doesn't have to be a constant. But I'm just going to use this definition, and you'll see why that's useful in a minute. So let's insert these into our Euler equations. So we get a d dt. So sorry if you're French or German. We're going to use the Australian Euler. So we should use Euler or whatever you prefer. But pardon my French, so the saying goes. So we're going to get a d dt delta rho. So I'm going to again kind of skip some of the details here because they're on your problem sheet. If you remember, we had a d rho dt plus div rho v equals 0. Now, so we can simply have, for example, a d dt that becomes a rho naught plus delta rho. But d dt of rho naught is 0, so we just get a d dt of delta rho here. And then we get a, well, this is going to be a rho naught v naught, but the v naught is 0. So we're going to get a rho naught delta v plus v naught delta rho and second order term. So that term is going to be 0, so it's going to leave us just with a divergence of this term. So we're going to get a divergence of rho naught, but the rho naught can come out the front. Plus, well, I'm going to put it on the right hand side actually, it's more helpful, is minus rho naught div dot delta v. All right, so that's our linearized continuity equation. We've dropped terms of second order and higher. And we're going to do the same with the momentum equation. So same with the momentum equation, we just get d dt of delta v dt. Now we had a v dot grad delta dot grad v. Now v naught is 0, so we're going to get v naught, and then we're going to get a v naught delta v. We get a so v naught is 0, so the only term left would be a delta v dot grad delta v, but that term's going to be 0 because we're neglecting terms which are second order. So the only term we're going to get left with in the momentum equation is simply the right hand side, which is the gradient of delta pressure on density. Another right way to think about this is you could put your density up on the left-hand side here. So imagine your density is up on the left-hand side. So the density on the left-hand side would be rho naught plus delta rho, but the delta rho term would be 0 because this is second order. So this would just be a rho naught left behind here. And so then we can just simply put that rho naught back on the right-hand side over here. So we're going to get a delta, grad of delta P on rho naught. All right, so that's, and we're going to assume no external forces. So this is our equation 1, and this is our equation 2. These are our linearized continuity and momentum equations. And for reasons that you'll see in a minute, we actually don't need to worry about the energy equation just yet. Well, we've already kind of gone through that because you've seen how I can get rid of the energy equation by defining the physics of my equation of state. So with this simplified equation of state we're going to use, but actually we haven't made any assumptions yet. We're just going to use this expression, and you'll see where this gets us. So, so that's what we've done. All right, I'm going to just keep going at the top here. Make a bit of space. So we're going to take our two equations, which are here, and we're going to try and combine them to get a solution. All right, so if you remember that we defined, that CS squared is delta P on rho naught, delta P on delta rho, sorry. So this expression here becomes a CS naught grad of delta rho. So we get, so this expression becomes a minus CS naught squared, well, grad delta rho on rho naught. Okay. But we could put that up on the left-hand side, so we get a rho naught d delta v dt equals minus sound speed squared grad delta rho. So that's our equation 2, but now you can see that, well, we've got a minus sound speed naught grad delta rho, we've got a ddt of delta v, and we've got a rho naught here. So if I take the divergence of this equation, and I take the divergence of the right-hand side as well, and I take the time derivative of this equation, so I take the time derivative of the right-hand side, then you should be able to see that I should get the same term here as I get here, and I should be able to cancel it. So let's do that. So we take the ddt of 1 and the divergence of equation 2. So we're going to do that. We get the following. So we simply get, this becomes a d squared delta rho dt squared equals minus rho naught, because that's a constant, so ddt of that 0, ddt of divergence of delta v. All right. And our second equation gives us a rho naught divergence of ddt delta v equals the divergence of this. So sound speed 0 is a constant. So we simply get del squared delta rho. Good. So this is, let's call this our equations 3 and 4. And we can simply substitute 4 into 3. Now I notice that the divergence and the ddt do commute because it's a partial derivative. This is a partial spatial derivative. So it's just like saying ddx, ddy. So don't be confused by the vector notation. If you are confused by the vector notation, sometimes it's helpful to write a gradient operator like the following. So it's a ddx dot is a divergence operator, for example. So you use the vector on the x down the bottom, so it looks a bit more like a derivative. That's really up to you, what notation you use. All right, but let's substitute. Let's get rid of one of our equations now. And you should see a little bit of magic unfold here. So we're going to get the following. We're going to get d dt, d squared delta rho dt squared plus minus. So we're going to get this term is going to be replaced by the negative of this term on the right-hand side. So let's put that on the right-hand side. It gives us a plus cs naught squared del squared delta rho. Interesting. So what does this look like? Well, it looks like 1 on cs naught squared d squared delta rho dt squared minus del squared delta rho equals 0. And you have seen this equation before. So that's simply the wave equation. All right, so the short answer is, so this means that small perturbations in density, they travel as waves because we have the wave equation. So we can see that the small perturbation, imagine we've got a fluid, its density is at rest, we've got a small perturbation in density, that thing will propagate as a wave with speed cs equals the square root of the ratio between delta p and delta rho. So we haven't specified what this ratio is, so we actually don't need to know what the equation of state is, but the sound speed will be given by this ratio. And so in terms of the mathematical definition, so hence our Euler equations are hyperbolic. And in fact, we can solve these equations. So let's go a little bit further. We know how to solve the wave equation. So let's do that. Well, we know what the solution is going to be. They're going to be solutions of traveling waves. But let's just show you how to get there. And this is a pretty common way of analyzing sets of fluid equations. And it's one we're going to see later on when we generalize to magnetic fields and dust and things like that. So we can solve the wave equation. Actually, we can do the same thing with, didn't matter if it was wave equations or not. But let's assume that the solutions are of the form of waves. So what do waves look like? Well, let's say that delta rho is just some Fourier series or some kind of combination of sines and cosines. So d is a constant, e to the I k dot x minus omega t. So where k is our wave vector here, so wave number, so that would be 2 pi on the wavelength, which has a direction, so it's a vector quantity. And, well, omega is the frequency, or the angular frequency. So omega is 2 pi times the frequency. Right, so in other words, we have a d squared dt squared. So this is going to give us, so a d squared, well, let's just do, so a d dt of rho is going to give us a minus I omega delta rho. So d rho dt is going to give us a minus I omega delta rho. D squared rho dt squared is going to give us a minus I squared. So that's going to give us a minus I squared omega squared delta rho I've dropped a sign here. What have I done? Gives us a minus I omega rho d squared gives us a minus, gives us a plus, sorry, I squared omega squared delta rho, yeah, which gives me a minus omega squared delta rho d squared delta rho dt squared. All right, so the same with the space part, then we're going to get a, so the grad of delta rho simply gives us, now the grad of this is just going to give us I k, so it's going to give us a basically dik, so it's going to give us, well, I k d, so it's going to give us I k d naught e to the I k dot x minus omega t. And then if I take del squared, so I take another gradient of that, that's going to give me a minus, it's going to give me an I squared, k squared, so it's going to be an I minus k squared delta rho. All right, so we've got these two expressions now for the time derivative and the space derivative, and we can simply stick these into our equation. And so therefore, well, let's call this equation plus. So plus becomes, we get a minus omega squared delta rho plus sound speed naught k squared delta rho, that's a squared, equals 0. So we can drop the delta rhos and we simply get that omega squared equals sound speed squared k squared. All right, so that's what you call a dispersion relation. It tells us how to relate the wave frequency to the wave number. And obviously now we can go back and just put that back into our expression for the density perturbation. So let's do that. And since the sound speed is positive, because it's the square root of something, solutions are simply plane waves. So for example, e.g., omega is plus or minus the sound speed kx, for example, in the x direction, e.g. in 1D. So for example, we have delta rho equals d naught e to the I. Now this is a kx, and x plus or minus sound speed t. So it's simply a translating wave, and if you want to just write that out again, so remember that's in like an a cos, kx, x plus or minus sound speed t, plus I, sine, dot, dot, dot. Right, so the solution is simply a sinusoidal wave that's just propagating in space with just a translation in space. So that's just a propagating linear wave. So the solution is a traveling wave. So if you take a fluid that satisfies these equations, a compressible fluid, you make a small density perturbation, that's going to propagate to you as a traveling wave. So it's a longitudinal wave, And that's exactly how I'm speaking to you now. I'm making a small density perturbation in the air, and that density perturbation is traveling to you at the speed of sound. But there's something more fundamental here. So it turns out that all hyperbolic sets of equations have the same kind of behavior. So we can consider in a coordinate system so let's imagine that you're riding the wave. So you've got a new coordinate which is simply x plus or minus sound speed t. The wave would appear unchanged. What do we mean by this? So it means, let's draw a little diagram. So this is time, and this is space. Then this is the line. So the wave front would propagate on a line which is a constant in this coordinate system. So this would be my line, which is x dash is x naught plus CST, and this is x dash is x naught minus CST. And so these lines, so basically that just means that, you know, if I'm riding on the top of the wave, I'm going to always be riding on the top of the wave if I move with the wave. So it's not a very special statement. This is x naught. It's my initial position, x naught. Sorry. And so these lines of constant CS, so these are known as the characteristics of the wave equation. And that's going to become important to us a bit later on when we're considering the nonlinear behavior, because these characteristics are the lines along which the solution is unchanged. And so that's going to be true. It turns out that this is a nonlinear property which is reflected in the linear solution, that you can find these lines on which the wavefront is constant even when the solution is not just a linear perturbation. All right, so there's one more thing to say here, is how to define the sound speed. So we've already covered the equation of state in the previous part of this lecture. So I'm just going to briefly cover how you can define the sound speed now. So remember, the sound speed was the ratio of the pressure perturbation to the density perturbation, square rooted. Right, so let's just cover the sound speed. So if you recall, the only thing we've defined so far is that the sound speed was defined as this, or the square of the sound speed was defined as the ratio between the pressure perturbation and the density perturbation. So for an adiabatic equation of state, we have P equals gamma minus 1 rho u. And that means that, therefore, that delta P is gamma minus 1 delta rho u plus gamma minus 1 rho delta u. All right, so, but we can relate u, so we can simply relate u back to rho. So we can say that delta u is simply equal to P on rho squared delta rho. And that's because, remember that our equation was du dt is P on rho squared d rho dt. So you can think of this equation, this is a Lagrangian perturbation, so you can think of this as just being a delta delta t and a delta delta t. And then you can simply drop the delta t. So that equation holds also for our perturbation theory here. All right, so in this case, we simply get, so therefore we can simply say that sound speed squared, so we get the pressure is gamma minus 1 P on rho delta rho plus P on rho delta rho, and that therefore tells us that the sound speed is simply times gamma times the pressure on the density. So in other words, the sound speed is the square root of gamma times the pressure on the density. All right, so that's quite a general statement, and that's the last thing we need. All right, so we're going to come back next lecture with some nonlinear behavior, but thanks for watching.